Newton's third law. Newton's third law states that for every action force, there is an equal in magnitude and opposite in direction reaction force. Note that action force and reaction forces act on different objects. Action and reaction forces always exist in pair. If forces F1 and F2 are equal in magnitude and opposite in directions, but they act on the same object, then they are not action and reaction pair. Examples of action-reaction pairs. Let's see a man sitting on a chair. There are 6 forces. Let F1 be the gravitational force on the man, which is the force exerted on the man by the earth. Very often, we call gravitational force is the weight of the body, the weight of the man. F2 be the force acting on the earth by the man. In this case, F1, F2 are action and reaction pairs. Because they are force on the man by earth and the force on the earth by the man. F3 be the force acting on the man by the chair. Which we often call it the reaction force on the man, or we say it is a supporting force on the man. F4 is the force acting on the chair by the man. Also, F3 and F4 belongs to action and reaction pair because they are the force on the man by chair and the force on chair by the man. Next, we have F5, which is the gravitational force acting on the chair, or we say it's a force on the chair by the earth. We often say this, the weight of the chair. Also, we have F6 is the force acting on the earth by the chair. Also, F5 and F6 belongs to action and reaction pair because it is a force on chair by earth and the force on earth by chair, which belongs to the same pair. Another example for action and reaction pair is the launching of spacecraft. When a spacecraft is launched vertically by a rocket, the rocket first exerts a downward force on the gas to push it downward. Which is called the force on the gas by the rocket. By Newton's third law, the gas exerts an upward force on the rocket to push it upward. Notice that the force exerted on the gas by the rocket is equal to the force exerted on the rocket by the gas. Example 1. A man pushes a huge rock by force F, and the rock remains at rest. He explains by saying that the force he pushes on the rock is cancelled by the force exerted on him by the rock, F pi. Is he correct? Explain briefly. Of course, he is incorrect, because the force exerted on him by the rock, F pi, is the force exerted on him, but not exerted on the rock. In fact, the rock remains stationary because the force he pushes on the rock, F pi, is cancelled or balanced by the friction acting on the rock by the ground. That is, F equal to frictional force. Example 2. In a tug-of-war between Peter and Paul, Peter won because he pulled the rope toward his side a certain distance. A student says that Peter won because he exerted a greater tension on the string than Paul does. Explain why he is wrong. He is wrong because the tensions exerted on the string by Peter and Paul are the same, which is T. Besides tension, there are frictional force acting on Peter and Paul. The friction on Peter is F1 and the friction on Paul is F2. Peter won because the frictional force on Peter, F1, is larger than the frictional force acting on Paul, F2. Therefore, we have a resultant force towards the left, which is equal to F1 minus F2. Hence, the whole system moving to the left. Example 3. A rock is on the ground. Explain whether the weight of the rock and the normal reactions on the rock are action and reaction pair. The weight of the rock is equal to the force act on the rock by the earth, which is the gravitational force of the rock, and the reaction force on the rock is equal to the force act on the rock by the ground. Even though R and weight W are equal in magnitude and opposite in directions, but since R and W are forces act on the rock, that is, act on the same object, therefore weight W and normal reaction R are not action and reaction pairs. Example 4. A card is put on the tables in figure A. When the fan is switched on, the card moves backward. Explain briefly. The reason is that when the fan is switched on, the fan exerts a force on the air. By third law, the air exerts an equal and opposite force on the fan. Which is to the left. So the force on the fan pushes the cart backward. In figure B, when a cardboard is now mounted vertically in front of the fan, and the fan is switched on, explain the motion of the cart. Now, the force on air by the fan is equal to the force on the fan by the air. So, the force on the air by the cardboard is equal to the force on the cardboard by the air. If all the air pushed by the fan is blocked by the cardboard, we have force on the fan by the air equal to the force on the cardboard by the air. Since the force on the fan by the air is to the left, and the force on the cardboard by the air is to the right, therefore they cancel each other. So the net force on the cart is equal to 0. Therefore, the cart is at rest or remains stationary. Example 5. A water rocket is partially filled with water and then pumped into air. The trigger is then pulled to release the rocket. Explain the motion of the rocket. When the trigger is pulled, the compressed air exerts a force on the water, and the water is then ejected with a high speed. By Newton's third law, the water will exert an equal and opposite force on the rocket, which is upward directions, and this force will make the rocket moving upwards. Let's see apparent weight in a lift. Inside a lift, a man stands on a compression balance. Let F1 Let W be the weight of the man. R be the reactions on the man. Let's find the apparent weight or the balance readings under the following conditions. First, the lift is at rest or moving with uniform velocity by F equal to ma. Since A equal to 0, therefore we have F equal to 0, R equal to W. Since R is equal to the apparent weight or the balance reading, therefore the apparent weight of the body is equal to weight W equal to mg. Case 2. The lift is moving upward with uniform accelerations A. A is larger than 0. If we take upward as positive, by F equal to ma, we have R minus W equal to ma, R minus mg equal to ma. Therefore, the reaction force equal to ma plus g, which is larger than mg. For case 3, the lift is moving upward with uniform deceleration. If we take upward as positive, we have A smaller than 0. That means A is negative. By F equal to ma, we have R minus W equal to ma, R minus mg equal to ma, hence R equal to mg plus A. But since A is smaller than 0, therefore we will get reaction force smaller than mg in this case, because A is negative. For case 4, the lift is moving downward with uniform acceleration. If we take downward as positive, then A is larger than 0. By F equal to ma, we have W minus m minus R equal to ma. W is mg minus R equal to ma, hence R equal to mg minus A, which is smaller than mg. For case 5, the lift is moving downward with uniform deceleration. If we take downward as positive, then A is smaller than 0. By F equal to ma, we have mg minus R equal to ma. Therefore, reaction force R equal to mg minus A. But because A is smaller than 0, that is A is negative, therefore we have reaction force larger than mg. For the last case, 6, the lift is falling freely. That means the acceleration is downward with A equal to g equal to 9.81 meter per second square. If we take downward as positive, then F equal to ma, we have W minus R equal to ma, mg minus R equal to mg. Okay, because A equal to g. Therefore, the reaction force becomes 0. Or we say the man is in a feeling of weightless, 無重狀態. From the above cases, we have the following conclusion. The apparent weight, balance reading, or the reaction will be equal to the true weight mg of the body when the lift is at rest or moving with uniform velocity. However, the reaction force R would be greater than its weight W when the lift is accelerating upwards or decelerating downwards. However, the reaction force acting on the man R would be smaller than the weight W when the lift is decelerating upwards or accelerating downwards. Also, notice that a person will feel heavier when the reaction force is greater than its weight W. That is, R greater than W. On the other hand, a person will feel lighter when the reaction force R is smaller than its weight W. That is, when R is smaller than W. Example 6. A man of weight 600 newtons stands on a balance inside a lift. A lift is going from the ground floor to the highest floor. That is, the lift is moving upwards. The graph shows the variation of the balance reading R with the time t. A. Describe the motion of the lift throughout the motion. From time 0 to 10 seconds, the reaction force is larger than the weight. Therefore, it is accelerating upwards. From time 10 to 15 seconds, reaction force equal to weight. That means the lift is moving with uniform velocity or uniform speed. From time 15 to 20 seconds, reaction force is smaller than weight. Therefore, the lift is decelerating upwards. For part B, applying the equations for case 1, we have R equal to mg plus A. That is 720 equal to 600 plus 600 over 9.81A. Therefore, A equal to 1.96 meter per second square. For case 2, reaction force equal to W. Therefore, acceleration equal to 0. For case 3, R is smaller than W. Therefore, R equal to mg plus A. We have 420 equal to 600 plus 600 over 9.81A. Therefore, A equal to 2.94 meter per second square, but it is negative. The negative sign means the lift is decelerating upwards. example 7, a block of mass 2 kg is tied by a string, and the string is connected to a spring balance, which is hung on the ceiling of a lift. If the lift is accelerating upward with accelerations 1.5 meters per second square, find the tension of the string and the reading of the spring balance. First, let's draw the force diagram on the block, which is the weight and the tension. By taking upward as positive, we have F equal to ma, T minus W equal to ma, T minus 2 times 9.81 equal to 2 times 1.5. Therefore, tension of the string equal to 22.6 Newton. Since the tension of the string is equal to the reading of the spring balance, therefore the reading of the spring balance is also equal to T, which is equal to 22.6 Newton. Notice that this example is similar to the cases that a man stands on a balance. The tension of the string in this example is identical to the reactions force acting on the man in the lift. T and R are similar. The last example, two blocks X and Y of masses 1 kg and 2 kg respectively are put together on a smooth horizontal plane and a force 9 newtons X on X as shown. Find the acceleration of the blocks. By F equal to ma, consider the whole system consists of the two bodies. We have 9 equal to 1 plus 2a. Therefore, acceleration is 3 meters per second square. For part B, find the force acting on y by x and the force acting on x by y. By drawing the force diagram on y and x, we have the force on x is the 9 newtons and the force on x acting on x by y, and the force on y is the force on y by x. Let's consider y. We have F acting on y by x equal to mya equal to 2 times 3, which is 6 Newton. Therefore, the force acting on y by x equal to 6 Newton. By Newton's third law of motion, the force acting on x by y is equal in magnitude to the force acting on y by x. Therefore, the force acting on x by y equal to 6 newtons. For part C, if the same force 9 newtons acts on y instead of x, that is, the force acts on these directions, how would the results in A and B change, if any? For part A, the net force is also equal to 9 newtons, which remains unchanged, and the total mass is 1 plus 2. Therefore, the acceleration of the blocks remains at 3 meters per second square. Therefore, the accelerations is unchanged. However, the force diagram on x and y will be different. For y, we have 9 newtons force to the left, and the force acting on y by x. For x, we have the force acting on x by y. By considering x, we have F acting on x by y equal to mxa, which is equal to 1 times 3, which is 3 newtons only, which is not 6 newtons now. Therefore, the force acting on y by x, which is equal to the force acting on x by y, they are the same. Therefore, force acting on y by x will be also equal to 3 newtons, which is not 6 newtons again.